In this example, we're going to be talking about motion in the gravitational field, which basically is going to have some physics kind of feel to it. So it says, suppose a stone is thrown vertically upward with an initial velocity of 64 feet per second from a bridge 96 feet above a river. It says, by Newton's laws of motion, the position of the stone measured as a height above the river after t seconds is this. So this is our position function, right? Where Ts equals 0 is the level of the river. So if we kind of look through these pieces, that value is going to represent kind of gravity constantly pulling down. The 64 is our initial velocity, and that 96 is our initial height, right? So just kind of a quick, like here's what's kind of going on that, and this is not the path of the object. This is the height with respect to time. So we had an object that was in the air, we threw it up, and then it came back down, right? So as time is elapsing, the object went up and it came back down, and that would represent the water, right? So somewhere it hit a maximum height because we were throwing it up and then it came back down, right? So that's kind of a rough idea. So when we get some of these answers, we're going to kind of try to connect it to our visual, make sure everything feels like it's supposed to be okay. So it says, what is the velocity and acceleration functions? So our velocity function, which is the derivative of the position function, is going to be negative 32t plus 64. Okay, so that is our velocity function, and then our acceleration is the derivative of the velocity, or the second derivative of the position function. So we're doing the derivative of this, and that's just going to get us negative 32. All right, so acceleration is our gravity constantly pulling us down. So we're going to end up using these now equations for a couple different questions. So what is the highest point above the river reached by the stone, right? So we're going to use calc. You could also use, you have a negative quadratic, so you could find the vertex essentially is what you're doing. And there were some couple different ways to find the vertex from previous math classes. We're going to do for the highest point, that's when we have a slope of 0. So that's when our velocity stopped, right? We had positive velocity because we have positive slopes, and then we have negative slopes. So somewhere when we transition from positive slopes to negative slopes, we hit a high point. So what is the highest point? We're going to be looking for when our velocity is equal to 0. So there's our velocity equation. So we'll take that equation, and everything in it represents slopes. And we would like to know when it equals 0. So we'll subtract our 64, negative 32t equals negative 64. We'll divide by our negative 32. And so we'll get when time is 2. Okay, so this is the when, right? But that's not the question. The question is what, not when. So from here to find the when part of, or the what part of this, we have the when. So our what part, what is the height? We have our position function. So we want to know what the position was at 2 seconds, which means we're taking negative 16 times 2 squared plus 64 times 2 plus 96. And if you throw that into the calculator, it's going to give you 160. And that was 2 seconds. And this is 160 feet. So it depends what they're asking for. If they're asking for when the maximum happened, great, that's that answer. But if they're asking for what is the maximum, then that's our answer. We have to take that value and plug it in. And then the last question is, with what velocity will the stone strike the river? So this thing is increasing its speed, and we want to know how fast was it when it hit the water? Well, we have a velocity equation. The problem is I don't know how long it took, so I don't know what time to plug into that, which that means we got to go back to a position function. So we got to do something kind of like we did here and then plug it into something else. So we want to know when the position hits the river, which basically means we want to know when our position is 0. Okay, which means we're going to be plugging, we're setting this equation equal to 0. Okay, so We have negative 16 t squared plus 64 t plus 96. We're setting it equal to 0. Hopefully it's factorable. We can take a negative 16 out. So if we divide that by negative 16, that'd be a negative 4. We divide this by negative 16, that'd be a negative 6. Still equaling 0. Anything multiplied to negative 6 that adds to negative 4? No. So unfortunately, we're going to need to do quadratic formula. So that's kind of our go-to to solve all of our quadratics. So this not factorable, quadratic formula. So we're going to be doing, we're going to try to take some smaller numbers rather than the big numbers. So we're going to be plugging in. So we're solving this. So we're doing, the reason we can do this, hold on real quick, is this is what we're solving, because if you're still solving this equation, you could divide by negative 16. And then that would just have this equation, sneak it in here, minus 4t minus 6 equals to 0. So the solutions for this is same as the solutions for this. We haven't changed anything regarding what our technically our x-intercepts would look like. This graph would just be steeper than this graph. So this would not be a representation of this visually, other than the x-intercepts would match. And that's what we're looking for. So if we plug this in, we're doing a negative b, right? Or a negative b plus or minus square root of b minus 4ac all divided by 2a. A is 1. So 2 times 1. So we are looking to do 4 plus or minus square root 16 plus 24 divided by 2. All right, so we'll plug that in, get our 2 answers, analyze that then a little bit. So we got fraction. We have 4 plus square root that adds up to 40 over 2. All right, so we get one answer, 5.16. And then our other answer, we'll do this again. This time we're going to do plus or minus, so the minus, negative 1.16. All right, so those represent our times of when we are at a height of 0. So this one makes sense. This one doesn't make sense. And that's because if you continued this graph, we would have a negative x-intercept. But for us, that's a negative time, and that one doesn't make sense. So that's how long it took to hit the water. So we use that now with our velocity equation. We would like to know the velocity at 5.16 seconds. And so that would be us doing negative 32 times 5.16 plus 64. And if we throw that all into the calculator, we would get a negative 101.12, and it's a velocity of feet per second. All right, so sometimes you have to do a little bit of side work before you can do the actual work. But that was a little bit of physics-ish kind of feel where we were taking first derivatives of position function, getting velocity functions, and then derivative of the velocity function, getting an acceleration function, to answer a couple questions.